Hello Chem 1B, this is chapter 14, lecture video 10, and this is the last lecture video of chapter 14. So after this lecture video, you will have finished the first chapter in Chem 1B. So let's talk about where we have a reaction mechanism that the first step isn't the slow step, or in other words, the rate limiting step. If that's the case, things get a little bit more complicated. So here's an overall reaction. Am I allowed to write a rate law for this reaction? The answer is emphatically no, because we cannot write rate laws directly from overall reactions. We can only write rate laws directly from elementary steps. If we went away and looked at experimental data for this overall reaction, we would determine that the overall rate law is equal to this rate law. Rate is equal to NO2 K times NO squared times Br2, which coincidentally is equal to the stoichiometry in this reaction, but that's just a coincidence. You can't take that as an absolute. This is a rare coincidence in addition. Let's say we propose this following reaction mechanism, where we have NO reacting with Br2 to form NoBr2, and this is a very fast reaction, so not our rate limiting step. And then NoBr2 reacts with NO to form 2NoBr, and this is a really slow step, i.e. the rate limiting step. When the rate limiting step is the first step, it's pretty straightforward because you don't have the possibility of any reaction intermediates in your overall rate law. However, when it's the second step, that's almost a guarantee. If we look at this reaction, we can find a set of reaction intermediates, and they are the NoBr2. They can't end up in our overall reactions rate law when we're developing it from our mechanism. So we know the rate limiting step is the second step because it's labeled slow, and I will always provide you with that information. This part, whether the reaction's fast or slow, that will be given. You don't need to be able to determine that. So let's go about solving this problem, trying to figure out, hey, this is the experimental rate law. Awesome. Well, is my mechanism possibly correct? If it is, it's the rate law I get from this mechanism has to be equal to this experimental rate law. Let's see if that's the case or not. Now, how do we do that? That's a little bit harder. The rate law is going to be based on step 2, which is the slow step. And this is my slow step. The rate law I can write from this will be rate is equal to K. We'll say K2 just for sticking with the labeling given in the problem, times the concentration of NoBr2 times the concentration of NO. Again, we always do this based on the reactants. Now, that's awesome, but there's a little bit of a problem. We can't stop here because this guy, NoBr2, is a reaction intermediate, and we cannot have our overall rate law depend on a substance that's not in the overall reaction, and reaction intermediates are not in the overall reaction. There's some other reasons as well. Reaction intermediates are very reactive and short-lived, so it's almost impossible to get a good reading on the concentration of NoBr2 during the reaction because they show up and disappear very quickly. And that means that this rate law is kind of useless if we can't determine one of the concentrations in it. It's not a very good equation because I won't ever know my concentration of NoBr2 to any level of accuracy. So how can we get rid of that reaction intermediate? So the way to do it is to look at that first reaction. We know that first reaction had these double-headed arrows. Now what those double-headed arrows means is that this reaction is in equilibrium. Now reactions at equilibrium, they're special. Now you might have learned some small things about equilibrium back in Chem 1A. We're going to learn a whole bunch more in the next 3 chapters of this class about equilibrium, and more than that even. Equilibrium is defined as when the forward rate of reaction is equal to the reverse rate of the reaction. So in other words, the rate of NOBr2 going back to the reactants here in this reaction is going to be equal to the rate of the formation of NOBr2. That's what it means when we have a system at equilibrium. So, what does that mean for our problem? Well, let's write out the rate law for the forward reaction. The forward reaction would be using these as my reactants. So, rate is equal to K1, we'll say, times the concentration of NOBr2, NO, times Br2. That's the rate of my forward reaction. Now, let's write out the rate law for the reverse reaction. So rate of the reverse reaction is going to be equal to K minus 1, and this isn't actually a negative sign or anything. This minus 1 is just a labeling convention. It's like the reverse of K1, and that's going to be equal to the concentration of NOBr2. This now is my reactant if the reaction's going back the other way, and that's why we use it in the reverse reactions rate law. Now, if we're at equilibrium, these two things can be set equal to each other, right? At equilibrium, we know rate F is equal to rate R. And so I can say, hey, K1 times the concentration of NO times the concentration of Br2 is equal to K minus 1 times the concentration of NOBr2. And since we're at equilibrium, I can divide by K minus 1 here on both sides and solve for my concentration of NOBr2. I can then take this relationship that we now have solved, NOBr2's concentration is going to be equal to K1 over K minus 1 times NO's concentration times Br2's concentration. This whole thing here, I can plug that in back into my rate limiting step reactions rate law in place of this. And that will allow me to rearrange and get rid of my reaction intermediate from my initial first rate law that I came up with for this problem. So let's do that. So here's that concentration term, and like we determined on the previous slide, the NOBr2 concentration is equal to K1 over K minus 1 times NO concentration times Br2 concentration. And we can plug all that in. And when we plug this into here, we get this setup. Now, K2 times K1 over K minus 1, that's a rate constant times a rate constant divided by a rate constant. In other words, a constant times a constant divided by a constant really just gives us another constant. So we can just write K here instead of all that. Now, technically, you should define K as K1 times K2 over K minus 1 here, so that when you plug it in to here, you're not changing any of the mathematics. But it works out. At this point, we have this NO times this NO. That simplifies to NO squared. And we get this overall rate law. So now if we go back to the beginning, we were told that the experimental rate law for this reaction was rate is equal to K times NO concentration squared times Br2. And according to this mechanism, our rate law that we proposed from the mechanism was equivalent to that, or consistent with it. This tells me that this reaction mechanism might be correct. It's not a for sure thing, because it's not the only thing that could be. I could come up with two mechanisms that both probably give the same experimental rate law, but are different. So you got to be careful with saying, hey, this mechanism is fully correct. No, we need to go investigate a little bit more, but this at least is a plausible reaction mechanism for this overall reaction. So let's do another problem. So we have this three-step mechanism, and we want to determine the rate law for the overall reaction, right? Again, our slow step here is step 2. So the first place we're going to start is by writing out the reaction mechanism for step 2. And rate is going to be equal to K, we'll call it 2 because of the 2 here, times H2O gas, H2, times N2O2 concentration. Now again, you might notice that we have another problem, because at the end of the day, N2O2 is a reaction intermediate. It's something that's formed in a first early step, in step 1 in this case, and used as a reactant in a later step, step 2. Because of this guy being a reaction intermediate, we can't leave our rate law here like this. We have to continue. Now, I could also ask, is there any other reaction intermediates in this reaction? And the answer would be yes, right? This is a reaction intermediate because it's formed and then used. N2O is also a reaction intermediate because it's formed and used. Cool. So we actually have 2 sets. Now the N2O one is not really going to be relevant because it shows up in the third step, which is a fast step, not relevant to our problem, but just something that you could also be asked about. So let's write this guy out. Remember, because we're in a fast equilibrium here, I'm going to say this is K1 and this is K minus 1 here for our rate constants. We can relate the rate of the forward reaction to the rate of the reverse reaction. So I can write, hey, my rate of my forward reaction is equal to K1 times the concentration of NO squared. And my rate of my reverse reaction, I'll use a different color here, is equal to K minus 1 times the concentration of N2O2, sorry. Now I can set these two equal to each other. In other words, K1 is times the concentration of NO squared is equal to K minus 1 times the concentration of N2O2. I guess to be consistent. Now again, I want to isolate N2O2 so that I can substitute it into my first equation here. Well, that again is simply just going to be divide over by K minus 1 here. So my N2O2 concentration here is going to be equal to K to the power K1 over K minus 1 times the concentration of NO squared. And I can take this whole bit and substitute it in to my original rate law. What I get is that rate is equal to K2 times K1 all over K minus 1 times the H2 concentration times NO squared. And I can simplify this a little bit more, right? I can say, hey, K is equal to K2 times K1 all over K minus 1. And just say, hey, my rate law is really K times H2 times NO squared. They don't always give us kind of similar answers like these last 2 examples have, but this is the process always if your slow step is the second step. And we won't be doing ones in the third or fourth step. Those get a little just too difficult. So let's look at some reaction coordinate diagrams for multi-step reactions. This is kind of important because there's more to it than what we saw in previous reaction coordinate diagrams. The more elementary steps in a mechanism, the more complex our reaction coordinate diagram becomes. here's a reaction coordinate diagram with 2 elementary steps in the reaction. And you can kind of see that now we have these 2 peaks in our coordinate diagram. This is due to the fact that we have more than 1 elementary step. So from the reactants to the top of the first kind of peak here is our activation energy of the elementary step 1. Transition state of the first elementary step is going to be at the peak. Then we have the delta H of our reaction between the reactants and products. After that, the peak of the second step is going to be our transition state of elementary step 2. And our activation energy will be this arrow going from the peak to the bottom of the peak, or the bottom of that part of the graph. That's our activation energy for the second step. Now, one thing I could ask is which step is probably the slow step? Is it step 1 or step 2? And the answer is going to be step 2. Now, the reason why is because if we look at the activation energies, this one has such a small activation energy in comparison to step 2. Step 2's activation energy is so much larger that it's going to probably be happening significantly slower. At the bottom here in between our 2 curves is going to be where we're forming our reaction intermediates. And so you should be able to label a coordinate diagram like this. If you have any questions, as always, just let me know. All right, so one last thing to talk about, and that's catalysts. I don't spend a huge amount of time on this. Really, catalysts do something very simple. They speed up a reaction. Most catalysts do this by lowering the overall activation energy of the reaction. Now, they can do that in a number of different ways. They do this usually by changing the reaction mechanism. So when you have a catalyst, your reaction mechanism is typically very different from when you don't have the catalyst. So currently, I have this drawing. Let's say the black line is without the catalyst. Once I add a catalyst, my new mechanism might proceed via 2 steps, right? Elementary steps, with significantly smaller activation energies. There are really 2 different types of catalysts that we can well, more than that, but the simplest separation of different catalysts is through homogeneous or heterogeneous. And really these just are based on physical state. A homogeneous catalyst is something that's in the same physical state as all the rest of the reactants in the reaction. And a heterogeneous catalyst is something that's in a different physical state from the rest of the reactants. All right, so this is the end of chapter 14. As always, if you have any questions, please let me know via discussion session or through email.